In this video, I will demonstrate LpBound, a cardinality estimator with one-sided guarantees. Cardinality estimation is the process of predicting the number of rows in the query output. For example, consider the following query that joins the two tables R and S on column X. We want to estimate the number of rows in the output of this query. Accurate estimates are critical for performance. Query optimizers use cardinality estimates to choose the best query plan. If the estimator predicts 1,000 rows, but the actual output is 100 times larger, the query optimizer may choose a suboptimal plan with poor performance. We propose LpBound, a novel cardinality estimation technique that provides guaranteed upper bounds on the cardinality. It supports queries with common features like acyclic and cyclic equijoins, group by clauses, and equality and range predicates. It is accurate and robust while keeping low estimation time and memory footprint. It is also explainable. We will look into this. LpBound uses degree sequences of the table. For example, given the table R below, the degree sequence degree y given x states how many y values are paired with each x value. In this example, it is 3, 2, 2, and 1. For this query, we compute the degree sequences for the tables R and S, degree y given x and degree z given x. They are shown as the two bar charts below. To get an upper bound of the join result, we consider the worst-case scenario. This is when values with high degrees in R are joined with values with high degrees in S, which is illustrated by the computation here. This provides a guaranteed upper bound on the join result cardinality. Working with whole degree sequences can be expensive. LpBound uses LP norms to approximate the degree sequences. This makes the computation more efficient. Some common LP norms include L1 norm, which is the sum of degrees, L infinity norm, which is the maximum degree. Other norms, like L2 and L3 norms, can capture the shape of the degree sequences from different perspectives. With only a few norms, we are able to capture the key properties of large degree sequences efficiently. We next give the intuition how the LP norms can be used to estimate the cardinality. We show the pipeline of LpBound. We first compute the LP norms for the degree sequences of the tables. Then they are transformed into information theory constraints. This is from a PODS 24 paper. Next, these constraints, together with other basic constraints, are fed into a linear program, which is solved to get the upper bound on the join result cardinality. The linear program can determine how much each constraint contributes to the final bound. This can then be translated into an explanation of the cardinality estimate. Now we demonstrate the interface of LpBound. In this panel, users can select the benchmark, that is, the database and the query. The query is shown here. This is a star query, where three tables movie companies, movie info, and movie titles are joined on the movie ID. There are also some predicates. We can set the LP norms to be used. The default is up to L10 norm. Our system has computed the estimation when the query is selected. The estimation error of LpBound and the competitors are shown in the table. The right panel shows the explanation of the estimation. This is the inequality that leads to the final bound, which is the product of four terms, summarized in the table below. For this query, the linear program has determined to use the L1 and L2 norms of movie companies, L3 norm of movie info, and L infinity norm of movie titles, and the weights of these norms. When the user hovers over the constraints, the exact information theory constraints used in the linear program are shown. The bottom panel shows the LP norms of the degree sequences. The red points are the norms used in the estimation. With this interface, users can easily understand the estimation and the constraints that lead to it. Finally, we explain briefly the experiment results. This box plot shows the estimation error of LpBound and the competitors for acyclic queries. The x-axis is the benchmark. The y-axis is the relative error to the true cardinality. Close to 1 means accurate, that is, the red line is the best. We can see that pessimistic approaches, including LpBound, are always above the red line, since they provide upper bounds. Traditional approaches, like Postgres, make the uniform assumption and thus might underestimate the cardinality. The machine learning approaches, including both PGM-based and NN-based, can be very accurate for job-like queries. This is the benchmark where they are tuned on. However, for other benchmarks, they are either hard to be migrated or have large errors. This demonstrates the effectiveness of LpBound. Thank you for your watching.